So we continue our discussion of reinforcement learning, but we're taking a step backward, and we'll talk about some fundamental tools in probability that helps us analyze policies and analyze how much time it will take them to converge in reinforcement learning. So last time we talked about the Hoeffling inequality and applied it to the analysis of a policy with reinforcement learning where the time horizon is finite. Now, as I said, we're taking a step backward. We'll talk about some measured concentration inequalities. Okay? So we start with the most fundamental one, which is the Markov inequality. Okay? So this is kind of related to some other things we talked about, which is Bayesian analysis, which is based on priors. So you have some knowledge about the world, subjective knowledge maybe, and you capture it with probabilities, and then you use the Bayesian conjugate or Bayesian theorem to come up with the next, once you see some data, to come up with your next belief system about reality. So here we don't want to have a lot of beliefs about reality. We want to have just very minimal beliefs. So it's a different way of capturing our notion about reality, but it's very minimal. And still we can say something about behavior, about our expectation of how the behavior will be in reality. And that helps us analyze things, but also helps us come to the conclusion that something is impossible. So these type of tools are used in statistical tests, because we can reach a conclusion that we're seeing something that is impossible. Okay? So now we're going to say, we want to say that the probability of a random variable, a positive random variable, is bigger than some positive number. It's also true for other numbers, but I'll concentrate on positive so that the explanation will be very clear. So the probability that a random variable is bigger than some positive number is less than or equal than the expectation. We assume the expectation is exists over A. So that's if we see if this is very small and we see it in reality, then we say it's impossible because we've seen an event that is that its probability is very small. So we end up reaching a conclusion that our model is not possible. So that's statistic testing, basically, essentially. Okay, so this is what we want to do today. Now, notice, as I said before, you just have two assumptions, very minimal. One is that the random variable is positive, and then the other one is that the average exists. That's always, this is our assumptions, nothing else. Okay? Very, very minimal assumptions.
What was the first one? First assumption?
That the random variable is positive.
Okay.
Just assumes positive values. Then, once we get this, we can look at the distance between the random variable and any random variable that is not necessarily positive, but has variance. So the distance between the random variable and its average. So we can look at the distance between a random variable and its average. Okay? We take to the power of 2, which is what? This is what? This is the variance, right? Okay? And this is now a positive This is a positive variable, right? So we can immediately apply this inequality to the distance of any variable to its expectation, which is the variance, and we get a better inequality. I'll talk about it next time. That is more useful. Okay? So first we want to get this, and then we want to apply this. Today we're just doing this. Okay? Okay? Good. So take the expectation. Now the expectation, this is the expectation, right? So we assume this integral is finite. Now this could be either a discrete variable with a countable number of values, or it could be like a density. So it could be a continuous distribution that has a density, but it doesn't matter. It's same principles apply. You'll see in the calculation. So this average, because the value is bigger than 0, is equal to this, right? And start the integral from 0. Okay? Now I can, if a is bigger than 0, I can separate the calculation of the average to the average from 0 to a and the average from a to infinity, the integral. And this is bigger than 0 because in this range x is bigger than 0. Okay? So I get that this is bigger than this integral, but I can, because x is bigger than 0, I can take a out and still get, so x is bigger than a, so I can take a out and get that this one is bigger than this one. Okay. So x in this range is bigger than a. So this integral is bigger than a times it's as if you take, at every point you take a instead of x.
Yes, but what about the first part?
It's positive.
But it can,
Okay, so it's bigger than this. Now what is the integral between a and infinity? That's exactly the probability of x being bigger than a. Okay? So you get this, and now divide by a, you get this. Okay? So for any positive random variable, it's true that the probability that x is bigger than a is less than the average over a. And that's called the Markov inequality. Next time we'll take this and insert this variable here. So we'll insert a new variable. You can try that as an exercise. Try to insert this variable here and see if you can understand what's the new inequality that you get. Okay? That's it.